Hi, my name is David, and today I'm going to be talking about the isolation and characterization of caffeine. As you know, caffeine to most people is a type of stimulant that keeps people awake. But to get down specific, it's part of the alkaloids family group, which basically contain nitrogen, as you can see from this picture. Now, to get even more specific, their biological activity has led to their thorough investigation in many disciplines. Now, how does caffeine work, you're probably wondering. Well, caffeine has a similar structure to adenosine. Now, adenosine has a lot of buildup inside the brain and regulates it. Adenosine binds to the brain receptors that cause drowsiness and laziness throughout the end of the day. Now, caffeine comes into the role because it has a similar structure to adenosine. Caffeine binds to the brain receptors and blocks the adenosine from building up, blocking the human being from receiving this drowsiness and laziness throughout the day. The purpose of this experiment is basically to isolate caffeine from tea leaves, to isolate caffeine through solid liquid extraction and liquid liquid extraction. Then caffeine will further be purified through the methods of sublimation. The three big chemicals that we're going to be working with are sodium carbonate, which may cause irritation to the eyes if touched, sodium sulfate, which also may cause irritation to the eyes, and methylene chloride, which may cause irritation to the respiratory tract and skin. The materials that we had to work with today involve a distillation system, as pinpointed by this picture. Also, our tea leaves, the sodium carbonate inside a light bulb flask with the water to filter out, the melting kit point to determine the caffeine, and another filtering system to extract the liquid from the tea leaves, and a sublimation system going on here. Now our first step in this experiment is to do distillation. But before we could start distillation, we add water into the light bulb flask with sodium carbonate to dissolve and heat it up to dissolve the sodium carbonate. Okay, after that we add tea leaves inside the light bulb flask, which will then start extracting the caffeine and all the other substances inside the tea leaves as well. The reason we have the H2 water jacketed condenser upright is because as the caffeine is being extracted from the tea leaves, vapor could also be going up. So we add water going in here, coming out here, to condense this vapor coming up to go back down. Now, the reason for the sodium carbonate inside the light bulb flask is because, in addition to caffeine, there's other substances inside the tea leaves that could that are not just soluble in water but also methylene chloride. For example, tannins. Caffeine and tannins are both being extracted from the tea leaves and are both soluble in methylene chloride and water. But we just want the caffeine to be soluble in methylene chloride to basically isolate it. So the reason the sodium carbonate is there is to produce protonation with the OH group inside the tannins to break down the tannins into a form where they won't be where they'll be insoluble in methylene chloride, just leaving the caffeine being extracted. Now that we have our liquid, now that we have our liquid from the distillation, we basically filter it out through this system right here, basically gathering all the liquid as possible and leaving all the leaves behind that were collected in the light bulb flask. Again, the reason we do extraction is to basically isolate the caffeine, which is collecting here in the methylene chloride, and basically removing that from the liquid on top, which has all the other impurities. Again, the tannins broke down into a form inside the top layer where they will be insoluble in methylene chloride. So all we're collecting is the methylene chloride with the caffeine inside this flask, Erlenmeyer flask right here. This process is done a total of 5 times to basically extract the most amount of caffeine as possible from the liquid above. So now that we have our methylene chloride with caffeine, there's still some water in there because water is also soluble in methylene chloride. So we use sodium sulfate to basically dry out the water inside the methylene chloride, so we just could have the methylene chloride with the caffeine. As we use our drying agent to basically remove all the water from the methylene chloride and caffeine, we're basically going to isolate the methylene chloride and caffeine to basically heat it up in this little system that we have going on here to basically evaporate the methylene chloride so we could just have the crude caffeine inside the flask. Now, caffeine has a very specific property that will let it sublime, basically stating that it could go from a solid straight to a gas form or a gas form straight to a solid form. As shown in this system, we sublime caffeine and basically we're allowing caffeine to be even further purified because caffeine is the only substance within this mixture right here that will sublime. We're able to further purify any impurities from and just isolate caffeine by itself on the pipette test tube as shown here. Now that we have our pure caffeine after sublimation, we're able to use a melting kit to basically check the melting point of caffeine and verify that if it's real caffeine or not. So in the we after sublimation we basically get our pure caffeine, which is as shown here, put it in a capillary tube, and we're gonna melt the other end of the capillary tube to basically close off this capillary tube because heating up caffeine can again cause sublime and will cause caffeine to basically turn into a gas form and evaporate out of the capillary tube. So we close the other end to basically liquefy this caffeine so nothing can escape and it'll turn into a liquid form. This will allow the student to check the actual melting point of their pure caffeine and to verify the temperature that it reached without it evaporating away. After the experiment, we were able to gather our data. So the tea leaves, we got a total mass of 1.59 grams. Now the crude caffeine, we got a mass of 0.0075 grams. Now for the pure caffeine, we got a mass of 0.0072 grams. Now the melting point of caffeine with the melting kit, the first trial, it started sweating at 210.3 Celsius. After then it melted at 227.5 Celsius. A second trial was performed, calculating to a total of 209.1 Celsius at the sweating temperature, and the melting temperature for the second trial was 228.2 Celsius. Now, averaging out the 227.5 and 228.2, we got an average melting temperature of 227.9 Celsius. From our data, we were able to calculate the crude caffeine in 1 gram of tea leaves. So from this formula, we were able to put the crude caffeine over the total amount of tea leaves, and we got a total of crude caffeine of 0.0047 grams of crude caffeine per tea leaves. Afterwards, we calculate the percent recovery for sublimation of the pure caffeine against the crude caffeine. So we put the final mass of the pure caffeine on top over the initial mass of the crude caffeine, times it by 100, and we got a total of 96% recovered after sublimation of pure caffeine. Here's an example of the HNMR of caffeine. As you can see from the picture, here's the molecule of caffeine, and each of the hydrogens are labeled corresponding to the graphs, which then correspond to the table below. Basically, the more upshielded the hydrogen is, the further away it is from electronegativity. So this hydrogen right here is further away from this double bonded O, which makes it the most upshielded. Now, this hydrogen here connected to the nitrogen is closer to the double bonded O's, which make it the second most upshielded. But this hydrogen right here that's connected to this end in between the two double bonded O's, and because of that, it makes it the third most upshielded as shown here. Now finally, this hydrogen that's connected here and shown here in the graph is within a ring, and it's in between two nitrogens, which makes it the most downshielded out of all the groups, correlated with the D. In this experiment, there are errors that were unavoidable or were technical in their procedure. For example, this extraction procedure in which methylene chloride was used 5 times to extract the caffeine to the utmost level from the liquid above could have caused problems. As you can see from this example is right here, the student didn't efficiently extract the liquid and had some of the layer inside the methylene chloride when extracting. Now this could have caused problem later on when purifying the caffeine. Additionally, the filtering system right here to extract the liquid from the leaves after distillation could have also caused problems because not all the liquid could have been drained, or some of the leaves were drained with the liquid down to the Erlenmeyer flask. And finally, the sublimation of the caffeine could have also caused problems. As you can see, when heating up the caffeine with the Bunsen burner, the caffeine was being vaporized, but because of the vacuum right here, the caffeine could have gotten solidified inside this little casket of the vacuum, and there would have been loss of caffeine there, which would have been unavoidable for the student. Some of these errors made a difference in the purified caffeine at the end of the experiment. And that ends our experiment of the isolation and characterization of caffeine in organic chemistry. I just want to reference the microscope techniques for organic chemistry and the Organic Chemistry 211 Isolation and Characterization of Caffeine by Jeff Bradbury of Cerritos College. And thank you for your time, and thank you for listening.